Learning targets. The first is to give a probability model for a random process with equally likely outcomes, and then to use it to find the probability of an event. And then second, we are learning about basic probability rules, which include the complement rule and the addition rule for mutually exclusive events. So we are looking at a problem today called the last banana. So my question to you is, who will win the last banana? So in order to understand this problem, we're actually going to start by watching a video, and this comes from a TED Ed talk where we are presented with this problem.
You and a fellow castaway are stranded on a desert island, playing dice for the last banana. You've agreed on these rules. You'll roll 2 dice, and if the biggest number is 1, 2, 3, or 4, player 1 wins. If the biggest number is 5 or 6, player 2 wins. Let's try twice more. Here, player 1 wins. And here, it's player 2. So who do you want to be?
Okay, so to recap what was explained in the video, there are 2 players. There's player 1 and player 2. Each player rolls a die, so 2 die are being rolled at a time. And if the largest value between the 2 is 1, 2, 3, or 4, then player 1 wins. If the largest value between the 2 is a 5 or a 6, then player 2 wins. Quickly, without thinking too hard about it, I'd like you to write down an answer for number 1. So who do you think has an advantage in this game? Would you rather be player 1, player 2, or neither? Make your best guess and explain your choice. Once you've done that, now let's think about this problem. So we want to figure out, is player 1 or player 2 more likely to win, or is it equal either way? So to do this, what we're going to do is we're going to play the game. So if you have 2 dice at your house, you can go ahead and just roll them and keep track. However, I am going to use a simulator from online. So I'm just going to go to random.org, and I'm going to select their dice option, which looks like this. So when you get to random.org, it's the option up at the top. It says games, and you want to choose dice roller, which will take you here. Now, I want to roll 2 virtual dice at a time, so I'm going to just keep track of which player wins. So here's an example. So I'm going to roll the dice, and I got a 4 and a 4. There are no ties in this game, because remember, the whole point is, of the 2 dice, what is the largest value? Well, the largest value here is 4. It doesn't matter that they're both 4. So that means that, in this case, player 1 wins. So on my paper, I'm going to put a tally mark for player 1 wins. And I'm going to roll again. Okay, now this time player 2 wins because a 6 is showing, and a 6 is higher than 1, so the highest value is either a 5 or a 6. So I'll put a tally mark on player 2. So what I'd like you to do is you are going to play this 20 times. So you need to roll the 2 dice 20 times and keep track of how many times player 1 wins and how many times player 2 wins. So you'll do that on this table in here. So keep track, just tally them up, make sure you don't go past 20. And then when you are finished with that, you're going to turn that into proportions for both. So you are actually going to stop after you play your 20 games, and then I will give you some class data so we can move on to the rest. Okay, so I filled in my data. So I played 20 times, and player 1, they were the winner 8 times. And player 2 was the winner then 12 times. So for A and B, I turned those into proportions. So I've got 0.40 and 0.60. Probabilities always add up to 1. So a valid probability model adds up to 1. Okay, and then I'm going to come down here for some class data. So normally what I would do is I would have you come up to the board and you'd write down how many you got. And then as a class, we would total all that up. I have some class data from doing this in previous years. And in this one, I'm just going to tell you this. I'm going to tell you the total for player 1 was 138 wins out of my class had played 320 times. So I'm actually just going to give you that, and I think you can figure out the rest from there. So now what I'd like you to do is you're actually going to finish up the entire rest of this page. So pause your video and work through, and then we'll add some things to the margins. All right, so let's go through this. So for 3A, I told you that before you left, it's 138 out of 320, which is about 43% or 0.43. Well, all I gave you is the number of wins for player 1. You had to figure out the number of wins for player 2. Well, we use this idea about probabilities adding up to 1. We've already talked about that before. Well, then how many times must player 2 have won? So in other words, how often did player 1 not win? So this idea here, these are called complements. And that is complement spelled with an E, not compliment with an I, not like you're so good looking. That's a compliment. Complement is like peanut butter and jelly. There are things that complement each other well, or they go together well. So the probability of player 2 winning comes from 1 minus the probability of player 2 not winning. So I'm going to put here on like not 2. Notationally, we write that as the probability of player 2 winning complement. This little C stands for to complement. So in this case, player 2 winning is 1 minus 0.43 to give me the 0.57. All right, then we want to figure out the true probability. Well, when we played this game, all these groups got different values, and I want to know what is the true probability of player 1 winning. So to do that, I had you list out all possible rolls that could have happened. So for example, we could have gotten a 1 and then another 1, and then a 1 and a 2, and so on. And you filled out this whole table, and then we're using it to find the probability of player 1 winning. So what I want to do is I'm going to look at my table and say, okay, well, this first one, 1-1, who wins there? Well, player 1 wins. So I'm going to highlight that. Player 1 wins for that spot. 1-2, who wins? Well, player 1 would still win. And in fact, player 1 is going to win all the way through here. They would not win if the 5 or the 6 are showing. So 1-5 and 1-6, they would not win. So what I notice here is on my table, like on these ones, player 1 would win, player 1 would win, player 1 would win. On all the others that are showing, player 2 would win. So I'm going to switch colors on that one. So all of these are when player 2 wins. So what are the chances that player 1 wins? Well, there are 16 outcomes here where player 1 wins. Out of the whole table, there are 36 possible outcomes. So I'm getting a probability of 16 out of 36, or 4/9, or 44% approximately. Now, that doesn't mean every time you play that exactly 44% of the time player 1 is going to win. This is, in theory, what we think will happen. So what I'd like you to do next to 4A is I'm going to write down here, this is a theoretical probability. And a theoretical probability is what we think will happen. It's based on some model or showing all possible outcomes and the number of outcomes that we wanted. So my theoretical probability is what I think will happen. In theory, 16 out of 36 times player 1 should win. However, we know that's not guaranteed. So all of these other probabilities up here, those are based on an actual action. We did something, we rolled dice. So these are called experimental probabilities. So experimental probabilities are found when you actually do something. So you actually roll dice, or you collect some data, or you keep track of how often something happens. So that's an experimental probability. The theoretical probability is based on a model or all possible outcomes and then how many we wanted. And then in part B, which was closer to the probability that we just found, that 44%? Was your group data closer, or was the class data closer? Probably the class data. And that is, again, because of the law of large numbers. We talked about that the other day. The more trials you do, the closer, now we can say the closer the experimental probability comes to matching the theoretical probability. Okay, one last thing on here, I do want to note this table showing all possible outcomes. This is called a sample space. And a sample space is a list of all possible outcomes. All right, awesome. So let's get some of our rules down. So some of our big important ideas today. The first thing is an idea about a probability model. And some of this will sound familiar. We've talked about similar ideas before, but a probability model is a list showing all possible outcomes. So we can also think of this as sort of a sample space. A sample space just shows all outcomes. A probability model shows all those outcomes as well as their probability. So it is a list showing all possible outcomes and their probabilities. Some rules for that probability model must add up to 1. So the probabilities all have to add up to 1. And then each probability is between 0 and 1. Okay, so when you're asked to justify whether or not something is a valid probability model, I'm looking for these two things. I'm looking for you to say that all the probabilities add up to 1, and then each probability has to be between 0 and 1. All right, then we have some just additional rules. One is this idea about a complement. And a complement is the probability of an event not happening. So notationally, what I'm going to put here is probability, so capital P, and then the event I put in parentheses behind it. I'm just going to call this event A. Well, let's say I want to know the probability of event A not happening. I'm going to put probability of A complement, and I can find that by doing 1 minus the probability of A. So that is our complement rule, is that if we want to find the probability something doesn't happen, we do 1 minus the probability that it does happen. All right, and then we've got one new idea that we didn't really talk about on the front page, and that is an idea about mutually exclusive. So what mutually exclusive is defined as is it's when events cannot occur together. So when you have two different events that cannot occur at the same time. So in our example with player 1 and player 2, player 1 and player 2 can't both win at the same time. I said there are no ties. So either one has to win, and that's it. We can't have any other possibility. There's no third option. Other examples would be like being a junior and a senior. You can't be a junior and a senior at the same time, okay? At least not according to the guidance office. They have you either listed as a junior or a senior. You can't be both. Now, if we know two events are mutually exclusive, then we have something called the general addition rule. And the general addition rule I think of as an OR problem. So you'll hear me talk about that a lot. I'm going to say an OR problem. That means if you want to find the probability of A or B happening, when those two things are mutually exclusive, well, that means you can just add up the probability of both. So if I want to know what's the probability that I randomly select from the high school a junior or a senior, figure out, okay, what's the probability I pick a junior, probability I pick a senior, and we add them up together. So when you have an OR problem, we think about addition. All right, please work through the check your understanding problem below and then hit play and we'll go over the answers. All right, so we've been given some information about the number of children from different mothers that had been selected. So in part A, we're asked, why is this a valid probability model? Again, you must talk about both of these things. So each probability is between 0 and 1. And then also the probabilities add up to 1. Make sure you actually double check though and make sure they do add up to 1. B, explain why events have one child and have two children are mutually exclusive. Well, you can't have both. You can't have just one child and you can't have two children at the same time. So I added in the term exactly, said you can't have exactly one child and exactly two children at the same time. So since these events cannot occur together, they are mutually exclusive. For C, D, and E, we're doing some calculations from our table. So on this first one, it says find the probability that a randomly selected mother has less than two children. Well, she has less than two children, that means she just has one. So I put on here the probability of one child, and that is 0.22. I found that from up here on my table. Find the probability that a randomly selected mother has 1 or 2 children. So this is one of our or problems. We already talked about how you can't have both at the same time. They're mutually exclusive. So this means I am going to add them up. So notationally, I wrote here probability of 1 child or 2 children. I just found both of those probabilities and added them up. And then in part E, find the probability that a randomly selected mother does not have 4 or more children. In other words, it is the complement of having 4 or more children. So when I look up here at my table, what I'm thinking about is, okay, well, 4 or more children, that's this group right here. So if there's a 13% chance or a 0.13 probability of having 4 or more, what's the probability they don't have 4 or more? That's everybody else. So I can also just think about it as I'm just adding up all of those sections. Well, instead of adding all this up, I can just do 1 minus the 0.13. So I've got on here the 4 plus children complement, and then I did 1 minus 0.3 and a final answer of 0.87.